Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where I talk about everything that I want to, science and math. And this is physical science, and we are talking about the kinetic theory of matter, which in solids, liquids, and gases. I was like, that's just the first section. Yes, that's right, solids, liquids, and gases. So this is the part of physical science where you start talking about chemistry. And what is the kinetic theory of matter? The kinetic theory of matter is that the idea that all atoms are moving, and they move more the more energy they have. Kinetic means movement, so like when you talk about potential energy and kinetic energy, potential energy is stored energy and kinetic energy is energy of motion. So you can imagine these little balls, atoms look like balls, we've seen them now with our electron microscopes, and just like how John Dalton said they would, and they move. Now, if they are in a solid, they just vibrate in their crystal lattice. So it's like a crystal pattern that they are locked into their position in this pyramid, and they just can vibrate. And they are vibrating. Like right now, this pen seems to be completely still, but the atoms are moving. And we know that because it's not super, super cold. It's not at absolute zero. That means it has energy and that those molecules are vibrating in their crystal lattice. Now, so it's sort of like that they're Legos all clicked in into their position, but they can vibrate in their position if Legos could do that. The book talks about that's like people at sporting events. When they're all sitting in their seats, they can move, but they have to stay in their seat. But then the next energy level up is liquids, and with liquids, they can move around each other. They're still very close, but they can move around each other. So the book says it's like when the fans are in the aisle, that they can scoot by each other. I always say it's like that in class, all the students are in their seats. That's like the crystal lattice. And then when they are moving around like the hall or something, they can say, excuse me, and slide by, but they're all very close normally. But this year we have COVID, so we're trying to spread out. So we're less like a liquid. And water in particular, the molecules are very attracted to each other. So they're kind of stuck together a little bit. They can slide by, but especially liquid water, that's why water balls up, while raindrops are teardrop shaped. Water clings itself, water gets a bead, like it beads up, all because water is very attracted to itself because it has a positive and negative side, and opposites attract. Now, the third state of matter that we're going to talk about right now is gas. And with gas, the atoms are far apart, they're moving very fast, so much that they don't really have an impact on each other. So they don't have those forces of attraction. So like if it's steam, water vapor, then they are not really going to cling together that much. They'll cling when they slow down and they condensate. But that is all. All right. Now, so how do you know the difference in a solid, liquid, and a gas? Well, a solid has a definite volume and a definite shape. So this is a solid. It has a definite volume and a definite shape. I could get its volume by putting it in water and seeing how much the water goes up, and then it has a certain shape, the shape of my pink Sharpie. For a liquid, it takes the shape of its container and has a definite volume. It doesn't just automatically fill up to the top of the container. Nope, it has a definite volume. So it doesn't have a definite shape, but it has a definite volume. If I drank all the water and I had gas in here, air, then air does not have a definite volume or a definite shape. It takes the shape of its container. It fills its container. Thermal energy is the connection between this kinetic movement of the molecules and temperature. So the faster the molecules move, the hotter it is. So to get the temperature, it is the average kinetic energy. Now, the thermal energy, the heat energy, is the total energy of the substance. So the heat energy of this would be all of the energy that's stored in the atomic bonds that can be broken. So one of the questions I always ask kids on test is, which has a higher temperature? A teacup of boiling water or a cool ocean? And the one that with the higher temperature is the teacup of boiling water. It has a higher average kinetic energy. But which one has more heat, total heat? And it's the ocean, because the ocean has all those bonds. This might be hot, the teacup of water, but the ocean has all those chemical bonds that could be broken, and that energy that is stored in those bonds released, and so it has more heat. So it's a little confusing because there's a difference in temperature and heat, and in our brains they're sort of the same thing in everyday language. I have to have some of that liquid while I'm talking. All right, so we talked about that, solid, liquid, gas. Talked about that. Okay, so let's talk about the phase change. So if something is ice, if it's a solid, and water's real easy because we're very familiar with it. You have ice, and as it heats up, eventually that energy of those molecules moving will get more and more and more, and they will break out of their crystal lattice and become water. Once it reaches where the ice starts melting, once it gets to that point of 0 degrees Celsius, 32 degrees Fahrenheit, even if you add heat to it, it will not warm up until all the ice is melted. So it is called sensible heat while it's heating up. It's called latent heat when it goes through phase change and it doesn't do temperature. So ice water is always 0 degrees Celsius. It's always 32 degrees Fahrenheit. And then once all the ice is melted, then it'll start heating up again. The water will get hotter and hotter and hotter until finally it gets to 100 degrees Celsius or 212 Fahrenheit, and it will start changing phase from liquid water to steam. And that will stay the same temperature until all the liquid water has boiled away. And then once it's steamed, then it can get hotter. So boiling water is always 212 Fahrenheit, always 100 degrees Celsius. And so once again, it goes through the latent heat, sensible heat thing. And I don't know if your book teaches those terms, but it doesn't hurt to go ahead and learn them. So what is boiling? You ever watched, you know the saying, a watched pot never boils, but you've watched it. And you see that before it boils, it'll get a little bubble down on the bottom, but it doesn't come up yet. What's happening is some of that water is getting enough energy to become a gas, but it doesn't have enough, and it's not a high enough temperature for it to overcome the atmosphere pushing down on the water. You're not aware of that you live in a sea of gas. You are in an atmosphere. There's gas all around you, nitrogen, oxygen, carbon dioxide, all these gases, and they're pressing on you. But you're used to it. You've always lived in this sea of air, so it feels like there's nothing there to you, just like probably to a fish, and they probably can't feel the water pressure either. Where you can, if you dive down in the bottom of the pool, you can feel it in your ears and stuff like that. To fish, it's just normal. Well, when that air, that atmosphere is pushing down on the pot, and the reason why it doesn't start bubbling up yet is because the pressure is not enough for it to overcome the atmosphere pressing down. And until the gas on the bottom and those little bubbles on the bottom of the pan get to be enough, then they can overcome that pressure and they can go up, and boiling point is reached and it starts boiling. And so that's what boiling point is. It's also called, to reach it is the heat of vaporization. Okay, remember how I said that gases fill their container? Gases spread out. They spread out as far as they can. They have lots of energy. They knock against each other with a lot of force, and they spread out. That is called diffusion. So when I was a new teacher decades ago, we will not talk about how many, there was in my physical science class, I think, maybe it was chemistry, it was a suggested demonstration for teachers, and it said to take a bottle of perfume and open it up, and then have the kids raise their hand as the gas diffused, and they could smell it, and you could demonstrate this. It was so stinky, and it was like, yeah, and then my room was stinky like that, and it just didn't work. You can do that. Go get some good smelling perfume like from your mom's and opens it up and have you and your brother smell when it goes around the room. But oh, I had some bad perfume and it was in my room and I couldn't get the smell out and it was giving me a headache. That was a bad day. Bad day teaching. I remember it all these years later. Okay, I talked to you about the heat curve. Up there it is, the sensible and the latent heat. Okay, now plasma. Plasma is a fourth state of matter, and this is a confusing thing because the science uses the word plasma to mean two completely different things. In biology, plasma is the straw-colored liquid that is your blood. You're like, no, my blood is red. If you take a test tube of your blood and you put it in a centrifuge, something that spins it around and around, it'll pull all the heavier material, the cells, down to the bottom, and it'll leave the liquidy part of the blood, and it's not red, it's straw colored, it's light yellow, and that is called plasma. So like if you go give plasma or whatever at the American Red Cross, that's what you're giving. It is a liquid. Okay, so that's the biology word for it. This is physics we're talking about in chemistry, and plasma is a fourth state of matter. It is found in the sun and other stars. It is found in fluorescent lights. It is a highly charged gas, and it's kind of weird. And you should read more about it, but it's interesting. So, like plasma. Now then, thermal expansion. Most things expand when they heat up. So you heat it up, it gets bigger. So that could be solid, liquid, or gas. Now, I used to have a demonstration though, because there was, I had this thing where it was a ball and a ring of metals, and metals will expand differently sometimes. Sometimes metals are tricky. And if you heated them up, if they were cold, the ball wouldn't fit through the ring. But if you heated them up, then it would go through because one would expand and the other one not so much, and then you could put it through. So, things generally expand as they are heated. Water. Okay, now water is weird. Most things are most dense as a solid, medium density as a liquid, least dense as a gas. But water is an exception. If water wasn't like this, we would have no life on our planet. Let me explain to you. Remember how I said that water is attracted to itself, that it has a positive side and a negative side and opposites attract? Well, when water is in the liquid phase, those positives and negatives, they are as close as they can get. They're very crowded. Water sticks to itself real hard. But when water goes to its crystal lattice, because of the geometry of water, it has to spread out for it to get into its crystal lattice, leaving a little air pocket in the middle of each of its crystal lattice units. So because of that, and you see some of that geometry in snowflakes. You should look at some of those on YouTube and or like Google it and look at pictures of snowflakes and stuff. And you can see that geometry that's based on 6. It's a 6-sided snowflake and stuff. But when it spreads out, it actually makes a little air pocket in the middle because it has to spread out like this, leaving a little gap. So that makes it where ice has air in it. And it makes ice less dense than liquid water, which is weird. But you've been around it your whole life, so it doesn't seem weird to you. If it wasn't like that, we would have no life on this planet. Now, why? It's because of the oceans. You know, all the life is based on the ocean. If the oceans died, then our planet couldn't support life anymore. And ponds and fish and all of the ecosystems. Normal things, when they do phase change from liquid to solid, they go from the bottom up, from the solid forming until the top, the liquid is last. But because ice is less dense, it'll be the coldest, 4 degrees Celsius, down at the bottom of like a lake or something. Then as it starts going into those crystal lattices, it spreads out and it floats up to the top because it has that air in it and it's less dense than the water. The molecules had to spread out. They're not as stuck together anymore. They've spread out, and then the ice floats to the top. So then all the ice is on the top. If it did it the other way, all the fish and stuff would be forced up and flopping up top, and die. But instead, the ice goes up to the top and the fish are down, and it makes an insulation layer. You know how air pockets, like you put air and things to insulate them. So all the fish are down here where it's cold, but they're fine. So it insulates them instead. And one of the many reasons why, if water didn't have the particular chemistry it did, we would have no life on this planet. And there's a whole bunch of it. This book might have a whole chapter on water. I'm not sure if it does, but the chemistry book does. So if you want to hear about everything awesome about water, there's a whole chapter on it in the chemistry class. So you can go watch it. Now, there are things called amorphous solids, and they are sort of like solids and sort of like liquids, non-Newtonian fluids. What this is these are things that act a little like a solid and a little like a liquid. And one of those, and a lot of times they respond to force. So like if you take cornstarch and put water into it where it's just wet, if you touch it gently, your hand will sink into it. But if you hit it hard, it becomes like a solid, and you can't. It becomes very hard. And you can even run across the surface. There's lots of videos on YouTube about this. But you should try it this week. You should play with that. Another one is silly putty. If you ever buy that silly putty, you know, it comes in an egg at the toy store. And you open it up and you pull it slowly. It stretches like chewing gum, but you do it fast and it snaps and breaks. Glass is like that. Glass is a lot of times where it is not, the molecules, if you can see them, it's a solid, but they are not organized in that crystal lattice. They are an amorphous solid. That is really interesting stuff, and you should do a little independent study and learn a little bit more. Another thing is liquid crystals. Liquid crystals are liquid, but they can respond to electricity where they get organized. And that is what you see in old calculator displays, a lot of things, where it's electronic displays, where especially ones that don't take very much electricity at all, watches, ovens, things like that. It is liquid crystal, and it responds to electricity, and it'll change with that. Now, properties of fluids. How do ships float? Okay. Now, so steel sinks. It's more dense than water, so it sinks. So how does the steel boat float? Well, it's the shape. You make the steel like this. It's mostly air on the inside, and so it can float. But how does this part of the steel, how does that float? And it's this. There is this idea of buoyancy, and the idea is that there is a force, an upward force, the buoyant force, that is equal to the volume of fluid displaced. I know that sounds confusing, so I'll break it down. Imagine this. And there used to be an old Beekman's World where they did this, and you might can find it on YouTube, and you should watch it if you can. Beekman was this mad scientist. He had a lab rat, Lester, and they would do all these experiments. But what he did is he had a phone booth. Y'all don't know what a phone booth is. It was looked like a refrigerator, but it was made out of plexiglass, okay? And the top was gone. Imagine a plexiglass refrigerator. It was filled all the way up to the top with water, and Beekman got in it. When he did, 1 Beekman's worth of water splashed out the sides. Can you imagine that? They got all the water and mopped it up. Lester did. He said, got to move displacing water. All I have to know is I move it from this place to that place, because Lester was having to mop it up. Then they weighed it. If the Beekman's worth of water weighs more than the real Beekman, then Beekman would float. If Beekman and the water weighed the same, he would be neutrally buoyant and just sort of float in the middle. And if Beekman weighs more than the Beekman worth of water, then he would sink. And that is the buoyant force. And so when you have that steel boat, it's pushing a boat worth of water out of the way. And this boat plus air on the inside weighs less than the boat's worth of water, so it floats. If you filled that boat totally up with cargo that weighed more than water, the boat would sink. So then there's this other idea of Archimedes. Archimedes was an ancient Greek scientist, and according to legend, which seems like it should be true. He was hired to find out if a king's crown was real or not. The king had given gold to the crown maker. The crown maker had made a crown and brought it back to the king, but the king suspected that the crown maker had cheated him and that he had just painted gold over lead and it wasn't solid gold, but he didn't want to cut into it to see if it was lead on the inside because that'd tear up all the artistry of his pretty new crown. So he gave Archimedes the problem of how can we find out if it's really gold and not lead without cutting into it. According to the legend, Archimedes was thinking about it at home, and he gets into his bathtub, and the water goes up 1 Archimedes worth. And suddenly he figured it out, how to do it. And he, according to legend, he hopped out of the bathtub, goes running down the street naked, runs right into the palace naked, runs right into the king's chamber naked. So, yeah, where he's having court yelling, "Eureka, Eureka," which is Greek for "I have found it." And I guess they forgave him for being so disrespectful as to running in. But, you know, scientists known for being kind of spacey and scatterbrained. And what he had figured out is that it could be density, that gold has a greater density than lead. And density is equal to mass divided by volume. So all he had to do was weigh the crown, get its mass, and then put it in water to get its volume, divide mass by volume and see if it's the density of gold, which is about 19 grams per milliliter, or if it's lead, which is way less than that, then he would know if it was gold or not. And from what I understood, it was not really gold, and that the crown maker was killed, was, you know, capital punishment, and that's the story that we've got all these thousands of years later. All right. Archimedes' principle. Okay. The next one is Pascal's principle, and it's just the idea that pressure is equal to force divided by area. And this is what you can remember this by. It is worse to be stepped on by a lady who puts all of her weight onto a stiletto heel, a high heel that, you know, the heel is only like that. Because she's got a certain amount of force, her weight, but being put on this tiny little area. And that will hurt more, and it's more pressure than if an elephant steps on your foot. Because an elephant has a great big foot, and it's over a big area, and it's not so much. It actually hurts your foot worse. And I used to teach with a teacher who, she had another job too. She worked at the public school I did, but on the weekends in the summer, she worked for the zoo here, Zoo Atlanta, and she worked with the elephants. And she said, yeah, she had been stepped on by elephants a lot of times, and you just shove them off. You hit them and tell them, get off, get off. She was an elephant worker, and she loved it. And she really didn't like teaching that much at the time. But later on, but she figured out that she liked middle school better than high school, and I think she went back to middle school and liked it. But when she was a new teacher, she was like, I just think I'm just going to go back and work with the animals, not the children anymore. I'd rather work with the children than the animals, just to let you know. All right, so okay, so there is another idea called Bernoulli's principle, named after Daniel Bernoulli. That's the joke that another physics teacher always tells. I know it's a bad joke, but there's just not that many physics jokes, so we got to tell them when we got them. But it is, and this goes against your brain, but you've seen it. It is that fluids, and that includes air. In physics, air and liquids are both considered fluids. That when fluids move fast, they make a low pressure, not a high pressure. And you're like, no, that's not true. Yes, it is. Okay, so let me explain to you. Imagine this is an airplane, and this is the bottom of the wing, and the top is curved. When the air molecules go over the top, they have longer to go than they do across the bottom. So when the air molecules split, they get more spread out here where they're moving faster than here where they're moving slower. Because there is more air molecules here, it creates lift, and that's how planes fly, on Daniel Bernoulli's principle. Other places you've seen it is umbrellas. You're walking along with your umbrella, the wind is blowing, making the air move fast across the top of it, and it'll cause a low pressure, and it'll get sucked inside out. It'll get pushed where it flips inside out. Another one is, you're in the shower. You turn on the shower, you got a shower curtain. You've got a fluid moving fast. which is a low pressure, and the shower curtain, that cold, wet, terrible shower curtain, will start coming in on you. Why doesn't it ever go out? Daniel Bernoulli's principle. So this is why I want you to do this fun with this. Get a hairdryer and either get some balloons, blow them up to be about that big, or ping pong balls, and turn it where the hairdryer is blowing full blast straight up. And you can put the ping pong balls into the column of air and it'll just float there. And then you can turn it sideways. So it's like, ooh, I'm doing magic. It's really science. There used to be a vacuum cleaner store who did this. They made their vacuum cleaners blow instead of suck, and in their display window they had bowling balls floating above the vacuum cleaner with Bernoulli's principle. So cool. And there's lots of other examples that you can see videos on YouTube. Take a look at it. But I want you to do it yourself too. All right, so we talked about fluid floating, and that's how Bernoulli's principle is how aerosol things work, because the fluid, the gas will move fast across the top when you spray it, and that causes suction that sucks the liquid out to spray. So that's how spray bottles work too. Okay, we talked about that. Okay, behaviors of gases. Gas pressure goes out in all directions. So if you have a balloon, the gas pressure goes out in all directions. If you add some more gas to it, then the pressure adds up. And that's the law of partial pressures, that all the gases in a group work together to be the total pressure. Okay, let's see if there's anything else we want to talk about. There is a relationship between pressure and volume. That if I have a balloon and I increase the pressure on it, I can decrease the volume. And if I decrease the pressure, the volume will increase. So it's an inverse relationship. There is a math problem to do with this. It's P1 times V1 equals P2 times V2. You can try that math. If that's beyond you, we'll be doing a lot of it in chemistry. You'll get to do it. And I even sing a song with it. It's the gas law song. I'm not going to sing it right now. You have to wait till chemistry. Okay, there's another one called Charles' Law, and it is that there's a relationship between volume and temperature. So if you have a gas and you heat it up, what happens to it? It gets bigger, right? That's how hot air balloons work. They don't put helium in hot air balloons, you know, the ones you see floating across the countryside. What they do is they put hot in it, which causes the gas in there to expand, making it less dense, and then it floats. So that's Charles's law. Would you ride in a hot air balloon? I used to say I wanted to, but as I'm getting older, I'm like, I don't want to run into a power line and get fried. I don't know. Maybe. I do the tethered one, but I don't think I want to do the one where you go floating over France anymore. I think I'm too old for that. All right, so that is our thing we were going to learn today. Come back and we'll learn some more chemistry, some more physics. Like, share, subscribe, and remember, science is great.